Alright, welcome to the class. We are going to start off Basic Analytics 101 session with the introduction to data and some statistical concepts. Now remember, you do not need a statistics or a mathematics background to understand this class and follow the training. However, it will be helpful if you have some high school level mathematics in your background and are comfortable with numbers. That said, we don't or we are not going to do any mathematical derivations or formula proving over here. You do not need to have a background in calculus, though it can help, but it is not a strict requirement to have a calculus or even an advanced mathematics background. We need just basic high school level mathematics up to class 10 to follow the full lecture series. However, it will always help if you have a predilection towards mathematics and you are comfortable with numbers and handling data. Now, starting off with our first concept of what I call is data projection. What do we mean by variables and observations? What do we mean by projection of a data onto an n-dimensional graph? And more specifically, what do we mean by parametric and non-parametric projections? Now, an example of a data set I'm going to pull out is a car sales data set. This is going to be a fairly common data set that we're going to be using throughout our training session. And I will also move on to a high school data set later in the class. This is an example data set in which we have a certain set of columns A, B, C, D, E, and so on, and we've got a certain set of rows going on from row number 2 in Excel all the way till row 154. Right now, how do we project this, or what does this data set actually mean, or what do we mean by rows and variables or rows and columns? Now, what these columns essentially mean, these are different kinds of measurements for each particular object. In this particular example, every object is a car, or I can say every row is a car. It's a car, it's one car, but each of these columns are different measurements of that particular object, or in this case that particular car. So can I say that these columns or these variables are different attributes or different parameters of a car? An example would be, let's say we've got a column or variable name which is engine S, or is going to stand for engine size in liters. So can I say engine size is a parameter of a car? Of course I can. So for example, for this particular car, the engine size is 1.8 liters. For the next, it's 3.2 liters. Consequently, horsepower is also a attribute of the car. Wheelbase, width, length, curb weight, fuel capacity, miles per gallon. These are all parameters of a particular car, right? And then what we see over here is the sales price of the car. Two particular columns which talk about sale and resale of the car, right? These could be any particular measurement. And then we've got what we the variable says manufacturer and model. This manufacturer tells us which company is making that particular car, and the model talks about what is the specific models. For example, we've got a BMW 3 series, we've got BMW 5 series. Within that, we've got 323, 328, and so on. We've got Buicks, Cadillacs, etc. So, in this particular data set, we've got certain features about a model of a car. We've got what is the engine size, etc., horsepower, weight. The type talks about whether the car is a sedan or an SUV. For example, Cadillac Escalade, it's a big SUV marked off as 1. It's a binary variable. Right now, we've got all these different kinds of variables which give us different dimensions or parameters of a car. Right. So what do we mean when I talk about data projection of variables and observations in an n-dimensional graph? Now pay attention because the n-dimensional graph is a concept that you're going to keep hearing again and again in this training, and it's very helpful in figuring out beginning itself what it actually means. An example, I'm going to talk about the n-dimensional. Let's talk about, let's say, horsepower and engine size. Right? If we had to project these two columns somehow, how would we do it? A very simple methodology for projection, and I'm going to draw it out over here, is when we project it on an XY plane. Right? So let's draw it out. Pardon my drawing skills, but we'll have to work with it. For example, let this be the x-axis, let this be the y-axis. So we've got variable 1 over here, and I'm going to plot variable 2 over here, right? So this is the origin, and I've got variable 1, variable 2. I can assign any particular variable on these two axes. This is the y-axis, this is the x-axis, right? For example, we talk about let's put horsepower on x-axis, let's put the wheelbase on the y-axis. I'm going to put in some hypothetical figures. Let's say the horsepower is 100 and the wheelbase is again 100. Then horsepower is 150 and wheelbase is, let's say, 75, right? And this is 0 0. Obviously I say this is 100, this is 200, this is 300, all the way towards infinity. Again, this is 100, this is 200, this is 300, all the way to infinity. Now if I want to figure out how do I plot this particular observation on an xy plane, right? Each observation in a data set can essentially be plotted as a single point on a plane or a three-dimensional space or a four-dimensional space. In this case, I have two variables which I'm plotting as two dimensions, the x dimension and the y dimension. I'm assigning horsepower as the x dimension, I'm assigning wheelbase as the y dimension. And this particular observation where horsepower is 100 and wheelbase is again 100, it could be millimeters or centimeters, this becomes a single point over here. So I identified this as a point where the horsepower is 100 and the wheelbase is also 100, right? Then I've got another point which says horsepower is 150 and wheelbase is 75. So where does horsepower 150 lie? It lies somewhere over here on this line, right? And wheelbase at 75 lies somewhere over here. So can I say this particular second observation lies over here, where I have got horsepower at 150 and I've got wheelbase at 75. So this is at 150, this is 75. So essentially I see that these two observations are plotted as 2 points on the graph, right? And once I plot them as 2 points on the graph, certain mathematical calculations can become very easy if I apply basic geometry towards them. For example, how far apart are these two observations? How far apart? I can measure them as the distance between these two observations. How do I measure the distance between two observations? If you can see now, I've got a perfect right angle triangle over here, right? I know what is the size of the base over here. The base is 50 points, right? And how big is the perpendicular? I know it's 25 points. 25 because I know this point is at 100, this point is at 75, so difference between the two is 25. I know similarly at point 1 it is 100, at point 2 x-axis is at 150. The difference between these two is exactly 50 points. Therefore, the hypotenuse, which is effectively the distance between the 2 points, I can apply Pythagoras theorem over there, which says, perpendicular square plus base square under the root, or hypotenuse. So which essentially talks about 25 square plus 50 square is the distance between these two observations if I am only plotting them on a two-dimensional space, right? So this tells me, if I have a third point, I've got another car which says, I've got 200 horsepower and I've got 200 wheelbase, which lies somewhere over here, right within my formula. Talk about that, right? So if I have to do certain comparisons, I call this as car A, I call this as car B, I call this as car C, and I ask an analyst, which of the two cars are the most similar to each other, right? And the two parameters that you're going to compare these three cars is simply horsepower and wheelbase, right? So how do you measure this? So one of the easiest method is that I find out the distance between the two observations, the distance between all the three observations, figure out which two observations are closest to each other. So the two possible distances I can figure out is distance between A and B, distance between A and C, and distance between B and C. And how do I do this? I do this by measuring the distance using geometric projection. Pardon my spelling if it's gone wrong, or let's say geometric progression. Sorry, I didn't mean the word geometric progression, but geometric projection is the right word over here actually. So I'm going to project it on a two-dimensional space. I'm going to carry out the calculations to figure out the distance between the three cars using Pythagoras theorem. And finally, I'm going to identify the pair which is the closest together. And in this case, I can say maybe, pair A and B are the closest to each other. Therefore, cars A and B are the most similar as compared to the third car when I measure them basically only on horsepower and wheelbase. Now, how do I take this forward? And in this particular data set, I've got so many dimensions, right? How do I scale it for more than two variables? How do I talk about three variables? If I want to talk about three variables, it's very similar, right? If I've got three variables, can I project them on a three-dimensional graph? X, Y, and I've got the Z axis over here. So I've got X axis over here, I've got Y axis over here, I've got Z axis over here. So we live in a three-dimensional space. We are all aware of that. You can look towards the corner of any particular room that you're sitting in, and the three edges that are going between the roof and the two walls, that's the projection of our three-dimensional space. Every angle is at 90 degrees to each other, right? So the Pythagoras theorem can actually be scaled up, or the Cartesian formula can actually be scaled up towards figuring out the distance between any 2 points. For example, I've got a set of observations again on X, I've got Y, I've got Z, and I've got observations X1, Y1, Z1 is one observation. I've got another two about X2, Y2, Z2, all the way till I've got observations Xn, Yn, and Zn. So I've got n observations, and I can actually plot them as n different points on this three-dimensional space, right? And again, I can apply the distance formula if I want to figure out the distance between any 2 points, and it's going to be the same. So if I scale up the formula, it simply becomes x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square under the root, right? So the distance formula or the Cartesian formula can actually be projected onto three dimensions. I've got a three-dimensional data set. Now if I've got four dimensions, how do I go? So how do I take care of the fourth dimension, right? Now that's a problem, because we live in a three-dimensional space. We can't even begin to imagine what a fourth dimension looks like, right? So a lot of movies would have covered this fourth dimension, but statistically or mathematically, what does it imply? So for example, I've got a data set over here. If I want to measure a car on horsepower, wheelbase, width, length, curve weight, fuel cap, now I'm going more than four dimensions. I'm going into multi-dimension or multiple variables. So how do I actually measure a car or project a data set which has got more than three variables onto an n-dimensional space? Well, fortunately, mathematics doesn't change the minute I add more than three dimensions. The basic mathematics will remain the same. While we cannot visualize a fourth dimension, it doesn't mean mathematically that it doesn't exist. So imagine n number of dimensions, all of them are at 90 degrees to each other, right? While we may not be able to see it, it's still there. So let's assume the fourth dimension is going to be x, y, z. I'm going to call it z bar, right? So it's simply the formula. If I want to do it again, I'll just simply add z bar 1 square minus z bar 2 square under the root, right? So x1, so I've got delta x plus delta y plus delta z plus delta fourth dimension plus delta fifth dimension plus delta sixth dimension all squared under the root. So it doesn't matter how many dimensions I've got, I'll simply add them into the Cartesian formula, right? And keep working with n dimensions. So every observation, right? So every observation that I have got, irrespective of the number of columns, I assume all of them are different dimensions, all of them are at 90 degrees to each other, and every observation becomes a single dimensionless point which I'm going to measure based on the variable. So let each variable be a dimension. So each point gets a coordinate in the n-dimensional space, which is simply d1, d2, d3 all the way till dn. So this set of points, this set of all of the observations in the data set, each of these observations becomes a single point in the n-dimensional space, and the address of that point, each point needs to have a mathematical address which refers to it uniquely, is simply the measurement in each of those dimensions. So this becomes d1, d2, d3, d4 all the way till dn for that particular observation, right? So that is how I'm going to project a data set having any number of variables from 1 till infinity onto an n-dimensional space, which will have as many dimensions as I've got variables, right? So that talks about projection of a data set on an n-dimensional graph. And again, why do we project it on an n-dimensional graph? Because we want to apply some mathematical formula onto a data set. What best way to do it than to apply geometry on it? To apply geometry, I need to put it into space, and that's how it is, right? So I realize, and you must also realize, that projection of data onto n-dimensional space is a very simplistic explanation. It holds well, but it's not something that you can apply uniformly across. So I'll again repeat this point, right? That projection of data onto an n-dimensional space provides us an opportunity to apply geometrical formula onto a data set and derive insights, do some analysis onto it. However, it is a simplistic explanation of statistics or mathematics on a data set. We're going to move on to parametric and non-parametric projections, right? For that, we're going to talk about the types of variables that we have, right? Now all types of variables cannot be projected as dimensions on a particular data set. For example, let's talk about another data set that I have got, an hypothetical data set where I've got for example, age of the person, I've got weight of the person, I've got height of the person, yeah, and finally I've got name of the person. So let observation 1, age be 30, let's say weight is 70 kgs, or if pounds if you want, you can put in a number which you like. Let's say height is 165 centimeters, and name is, let's think of a weird name. Let's say name is Darth Vader. A very puny looking Darth Vader indeed. Let's say second person, age is, let's say 35, weight is 80 kgs, height is 170 centimeters, name is name is Batman. All right, and we've got n number of observations over 1, 2, 3, 4, 5. We've got Darth Vader, we've got Batman, we've got Spider-Man, we've got He-Man, we've got Skeletor, we've got n number of people over here, right? So I'm measuring them on their age, their weight, their height, and their name, right? All of these are columns, all of these are variables, right? Now projecting age, weight, height is going to be very similar. It's going to be very simple. I put age on one axis, I put weight on one axis, I put, let's say, height on an axis. The problem arises with the name, right? How do you project names on an axis? Do we provide names like, let's say, this is the origin, let's say hypothetically name is an axis over here, right? Can I say the at origin you have no name, you've got 0 0, right? At this point the name is Darth Vader, at this point the name is Batman, at this name the name is Spider-Man. Does it even make sense? Why it doesn't make sense is because we've got this particular arrow running over here. What this arrow says is that the value at this point is always greater than the value at this point, which is always greater than the value at this point. So does it mean that Batman is greater than Darth Vader, right? And which is smaller than Superman? It doesn't make sense. How do you measure name? How do you give direction to a name? How do you even figure out the distance between two names? It can't be, because name, while it is a measurement, it is a variable, it is something which is the property of a person over here, right? It's not a variable in the sense that it can be projected onto an axis. Can you think of more examples of variables which can't be easily projected onto an axis, right? For example, what is the color of the shirt of students in a class? For example, this could easily be in a classroom data set. We've got students who age 30, 35, 25, etc. We've got weight, height, name, and you've got the kind of shirt they are wearing. They could be wearing red, blue, green, etc. Right? How now these are also variables. We are measuring the student, or we are measuring each observation based on the color of the shirt. right? So this is data, and this data can be useful depending on analysis. If I want to figure out, which is the most popular color, which is the most soothing color, does color of the shirt have got anything to do with the psychological makeup? Do serial killers specifically wear a certain type of a color of a shirt, right? So color as a variable is important, right? But how do I project it? How do I project a data set which is categorical in nature, right? If I project data, for example, let's take a clean screen, right? I want to project color again, right? Can I say, color going over here, it's red here, it's blue here, it's green here, and so on, right? Which essentially tells me, if I plot it this way, right, green is larger than blue, which is larger than red. That's not true. No, we can't actually measure. So some data points, or some columns, or some variables cannot be projected, right? Typically variables which do not have any magnitude or direction. I screwed that up. So here, direction, right? So no magnitude, no direction are typically called as categoric variables, right? Let's talk about this data set again, right? Can you give me an example of what is a categoric variable over here? It's very simple, right? The manufacturer and model observations, these are categoric variables because they do not possess either a dimension, or they are dimensions of a car, but they do not measure or they do not have any direction or magnitude. For direction, I can always say, horsepower 140 is less than 225, which is greater than 210, and so on. In horsepower, I can actually figure out the direction and also the magnitude. By magnitude, I can essentially tell the difference between two horsepower is simply, a arithmetic operation. The similar thing goes for engine size, the wheelbase, the width. These are all measurable attributes. They have direction, they have magnitude, which tell us the difference between the two, right? But you can't do a direction or magnitude between Park Avenue and an El Dorado, right? For example, El Dorado minus Park Avenue does not give you a Lee Sabre or a Regal, right? If I add up a Century or a Regal, I won't get an Escalade. No, it doesn't work that way, right? While you can add up a two wheelbases and figure out what is the combined wheelbase as a number, it may or may not make sense, but you can do it. Similarly, if you add up these two numbers, you get sum as 365, which essentially means 365 horsepower. That's the combined output of these two cars, right? But can I say, A4 plus A6 gives me an A10, right? It doesn't work that way. It doesn't mean anything, right? So on these variables, we can't do any arithmetic operations. We can't do addition, multiplication, division in any meaningful way, right? This is because these are categoric variables. So again, going back to the types of variables that we have, right? So we've got something which we call as nominal scale, or it's also called as the categoric scale, which talks about things which have neither magnitude nor direction. For example, color, region, type of car, etc., right? Ordinal scale, right? That's the next measurement. So moving on to the next type of variable that we have, which is ordinal scale, right? So ordinal scale variables refer to those variables which have got direction but don't have magnitude. An example of the kind of variable that can have direction but no magnitude can be, for example, shirt sizes. Now, typically, shirt sizes follow a universal sizing methodology, which can be, let's say, small, medium, large, extra large, and maybe very small. Right? Now, these kinds of variables, we can say are they categoric variables? Right? They do seem to be categoric variables. For example, small is a category, medium is a category, large is a category. They don't tend to have any kind of magnitude in them, but there is always direction over here, right? We do know that an XL shirt is larger than a large shirt, which is again larger than a medium shirt, which is larger than a small shirt, and so on, right? The question is how much, by how much, right? how large is a Excel larger than a large size, and how do you even measure large versus small, right? We do know, okay, a shirt is pardon my shirt making capacity over here. So this is a small shirt, and I've got a big shirt over here, and so on. I'm going to not make this shirt diagram. It's coming out very, very weird, right? I'm just let me gonna undo this, right? But you get the point that does a large minus medium, will it give me a small, right? Does a very small plus small give me an extra large, right? They don't, right? We can never know, or we can't do any kind of arithmetic calculations on these variables, but I can always order them in certain directions. I know that small is less than extra large, right? The third law will still hold true. If medium is greater than very small, and large is greater than medium, then large will also be greater than very small, right? And why we can say that? Because direction is maintained. Can you give me some more examples of where we might have ordinal scale where you have direction but not magnitude? For that, I'm going to take you to the next example data set that we're going to be working with, the HSB data. This is an example of high school data, which is a very popular data set to demonstrate the power of significance test, which we will be doing in the next few classes. I'm going to take you through the data dictionary for this particular data set. This is a data set of about 200 students. We have the ID for each student. As you can see, ID is a numeric variable. But I'm going to ask you later on to try and classify this. What kind of variable you think this is, right? We've got a gender variable, which we call it as simply as the female variable. Binary, it is 0 or 1. 1 means female, 0 means male, right? Then I've got a variable which is race, right? Race over here stands as the ethnicity of the students in American data set. So you've got the prevalent ethnicities in America represented in this data set. 1 stands for Hispanic, 2 stands for Asian, 3 stands for African American, 4 stands for white, right? Now, another point which I wanted to make about categoric variables is the concept of recodes. If I recode a categoric variable with a number, does it actually change its figure? Does it change its type? For example, we've got in this data set, we've got race, and we've got Hispanics, we've got African Americans, we've got whites, and we have Asians, right? Now, this is a categoric variable very clearly, right? It does not have direction, it does not have magnitude. We can't do Asian minus white will give us an African American, or a Hispanic plus white is equal to Asian. It doesn't make sense, and no need to crack any jokes also. But strictly speaking, this is a categoric variable, does not have no direction, no magnitude over here. But if I do recode this as, let's say, H is equal to 1, African American equal to 2, white equal to 3, Asian equal to 4, or any other kind of recoding a technique, it could be 1, it could be 10, it could be 100, all of them could be 2000, this could be 3500, whatever number, right? And why do we do recodes? This is a database concept, right? It makes it easier to store data. Instead of storing the full character variable as Hispanic, and it repeating hundreds of times, similarly with Asian or African American, etc., right? In databases, the longer the point that needs to be captured, the longer the data field, the more memory it takes, right? And if the same data set, the same point is to repeat multiple times, there's no need to write Hispanic again and again and again, or Asian again and again in the data set. What if I recode it as 0, 1, 0, 2, 0, 3, and I maintain a master table somewhere else, where I have H is equal to 1, African American is equal to 2. This is the master table which repeats once. Then I have the full data set in which everywhere where it's Hispanic I write it as 1, if wherever it's an African American I recode it as 2, and so on, right? So while over here it's clear that the ethnicity has been recoded as 1, 2, 3, 4, right? This does not convert it into a number variable which has got direction or magnitude. It still remains a categoric variable. So race is still a categoric variable. Recoding a category as a number does not change its character. It does not change its meaning, right? You still can't sort in any meaningful way with direction or magnitude on race, right? You can't do arithmetic operations on it. You can't calculate things like the mean race, right? Now the third variable that we have got over here is the socio-economic background of the student, purely in the kind of income level of the family which they are hailing from, and we've divided it into low, medium, and high, right? And again, it has been recoded as 1, 2, 3. Now socio-economic background, right? So we've got the SEB variable, right? 1 is low, 2 is medium, 3 is equal to high, right? This talks about the income level from which the students are hailing from. As you can observe, and it's fairly clear that this variable also has got direction, right? We know that socioeconomic background high is in terms of economic terms greater than medium, which is again in economic terms greater than low, right? So there is direction in this variable, some kind of direction, but there is no magnitude, right? So magnitude is not present on this variable. We can't say, low plus high is equal to medium, right? We don't know, right? Medium minus high is not equal to low. Low plus high does not give us equal to medium, right? There is no magnitude involved. There is direction over here, right? So this kind of variable is also an ordinal variable in this data set, right? Coming back to this data set, we've got the type of school the student is attending, whether it's a public school or a private school. Again, recoding public equal to 1, private equal to 2. This does not give us direction, neither does it give us magnitude, right? Private is not greater than public, public is not greater than private. We don't know the difference between public and private in terms of mathematical terms. This is a pure categoric variable. The type of program the student is enrolled in, general, academic, vocational. Again, no direction, no magnitude, right? Then we have the variables, which is the read score, the write score, the math score, the science score, and the social studies score. So these are exams which the students have been subjected to, right? And these are the scores which the students have obtained in their exams, right? Now this kind of variable does have direction, does have magnitude, right? So what are these variables? The one which we discussed in car sales as well. All of these variables, they've got direction, they've got magnitude. Again, in the HSB data set, the scores of the students have got direction, they have got magnitude, right? We call these kinds of variables as ratio scale variables. For example, height, weight, all kinds of specific measurements, they can be called as direction and magnitude. So the three kinds of variables that we've just studied now, so I'm going to reiterate them on the white screen, right? We've got the nominal variable, right? Nominal or categoric variables, right? Then we've got ordinal variables, then we've got ratio slash continuous variables, right? So they have got no direction. So nominal or categoric variables, right? If we talk about direction and magnitude, right? So they don't have, or I just made this a little wrong, let me do it again, right? Yeah, there it goes. So I want to classify them direction, magnitude, right? So nominal or categoric variables, no direction, no magnitude. You can't do any arithmetic operations on them. Ordinal variables, direction but no magnitude. So you still can't do arithmetic operations in them, but you can sort them ascending or you can sort them in descending order based on the measurement that we want to use. Ratio or continuous variables, direction is there, magnitude is there as well. You can sort and you can do arithmetic operations, you can plot them on graphs. So the ratio and continuous variables are also known as parametric variables. Why are we calling them parametric variables? Because they have direction, they have magnitude, and they can be projected onto the n-dimensional space easily without any particular assumptions in place, right? Ordinal variables, they have direction but they don't have magnitude. So strictly speaking, they cannot be projected on the n-dimensional space. Nominal and categoric variables, neither direction nor magnitudes. There's no way I can use this as a vector. These also cannot be projected on the n-dimensional space, right? So while we'll talk about workarounds, how to get them into the n-dimensional space, but that's for later. For now, only ratio and continuous variables are on which there is direction, there is magnitude, and I can project them on the n-dimensional space. That leaves us with the fourth variable, the interval scale. While the interval scale may sound like having intervals, it doesn't really mean the kind of intervals that you may be thinking. Interval scale variables are a special class of variables. They don't occur very often. You are very unlikely to actually uh, sort of come across them. The very definition of an interval variable is a variable which does have direction, which does have magnitude. So both direction is there, both magnitude is there, right? But you cannot, you are limited with the kind of arithmetic operations that you can apply on them. A very common example of an interval scale variable is a temperature scale. Temperature as a variable. For example, I'm sitting in an air conditioned room. Right now the temperature is, let's say, 25 degrees Celsius, right? If I increase the temperature by 10 degrees Celsius, it becomes 35 degrees Celsius, right? Now 35 degrees Celsius is warmer than 25 degrees Celsius, right? So I know there is direction, right? And it is warmer specifically by 10 degrees Celsius, right? So I know there is magnitude involved, right? But can I do certain operations like, what would be twice as hot as 25 degrees Celsius, right? Can I make my room twice as hot, right? The operation is twice as hot. So what would be the temperature of the room if my current room temperature is 25 degrees Celsius? I have to make it twice as hot. So those of you who are saying that twice as hot should be 50 degrees Celsius, right? Well, you are mistaken. Twice as hot of 25 degrees Celsius is not 50 degrees Celsius. For example, if I convert 25 degrees into Fahrenheit, right, and 50 degrees into Fahrenheit, right, would that still have the multiply by 2 relation between them? It most certainly will not. For example, if it was freezing right now, which is 0 degrees Celsius, right, what's twice as hot, 3 times as hot, or as 100 times as hot? It would still be 0 degrees Celsius if you're doing a multiplication over here, right? So multiplication division does not work very well on interval variables. Why doesn't it work well? Because we are assuming the origin of 0 degrees Celsius an actual origin, right? For example, if I am plotting temperature on a scale, right? For example, this is the x-axis, right? This is the origin. If I say this is 25 degrees Celsius, right, then 50 degrees Celsius should technically be same distance from origin as that point from 25 degrees. So I take this point over here, this is the measurement, I plot the exact same distance, and which comes to be 50 degrees Celsius over here, right? But how do I know what the origin is? Is the origin 0 degrees Celsius, right? It's not. 0 degrees Celsius is simply an arbitrary scale which I've put in as on the lumber line and say this is 0 degrees Celsius, right? 0 could be here, 0 could be here, 0 could be here, right? In the temperature scale, 0 degrees Celsius is not the origin. The origin is somewhere over here, which is 0 Kelvin, or which is minus 273 degrees Celsius, right? So it's way off over there. 0 degrees Celsius and 0 degree Fahrenheit are actually points on the scale. They are not the origin. Therefore 25 degrees Celsius is not the distance from 0 and 25 that we need to take into consideration, right? So in this particular case, while there is direction and magnitude, 50 is greater than 25 and it is greater by exactly 25 degrees Celsius, right? We still don't have a very clear or fixed origin of measurement. Another example which I want to talk about for interval scale is very simple. It's shoe sizes, right? Let's talk about UK shoe sizes. For example, I'm a UK size 12, right? Does that mean a size 12 shoe size? Does that mean a size 6 is exactly half of 12? Is it? It's most certainly not. 6 is not the half of 12. That means a size 12 shoe does not incorporate two size 6 shoes. At most, a size 12 shoe is maybe, half as big as a size 6 shoe. And why is that so? Because the way the shoe size scale is structured, it starts with an arbitrary children size, 5, children size 6, it goes all the way to children size 12. And then you start with adult size 3, then you start with adult size 4, and you have got adult size 12, right? So where the origin is obviously over here, which is 0, right? Adult size origin, if you extrapolate it, starts from here, right? So when I say 6, which is somewhere over here, right, and I say 12, which is somewhere over here, 12 is the double of 6 if measured from the origin of 0, right? But the actual 0, which is no size at all or no length, is actually over here, right? So 0 to 6 is this measurement over here, right? And if I double it, it's going to go way above and beyond size 12, right? This is again because there is confusion regarding the origin or what is actually 0, right? Whenever there is a confusion regarding the true origin of a particular measurement, even if you have direction and magnitude, you can't do all sorts of operations. There are some limitations. Why? Because that's where the interval scale measurement comes into play. Now, to be frank, we've talked about two examples, which is shoe size and temperature, for being the interval scale variables. They are not very commonly occurring in our data sets. You are unlikely to come across too many of interval scale variables, and most of the assumptions of actually continuous or ratio scale will continue to work with interval scale as well. Alright, so we've got four kinds of variables. We've got nominal or the categorical variables, no direction, no magnitude, pure categories. Ordinal scale, some direction but no magnitude, right? So you have order in the variable, sizes or grades. Then you've got the interval ratio scale where you have got direction, you've got magnitude as well, right? So now in our next particular lecture, we're going to talk about the kind of measurements that we can do across these kinds of variables, right? So now please have your statistical programs open and ready. We're going to be working on SAS, we're going to be working on SPSS, we're going to be working on Statistica, and I'm also going to pull up our statistical package and talk about the various measurements that we can do and start manipulating these two data sets that we have in actual statistical packages. All right, so on to the next class.